Hello everyone, welcome to this online course on material science. This is lecture 13 in the module 1 on magnetism. Today I will start talking about paramagnetism. So the intuitive picture that one should have in his mind about paramagnetism is that, let's say we have some material, right? And inside that piece of material we have a number of ions or atoms, right? Let's say we have 4. For the ease of this discussion, and every one of those atoms or the ions will have some magnetic moment, right, which is a vector, and they will be directed in different random directions, right, without the absence of any external magnetic field. Now we want to study this paramagnetic material under the influence of some magnetic field, right? Let's say we put this material between a north pole and the south pole of some magnet, right? So the magnetic field lines will be in this direction. So the magnetization is along this direction, right? Now what will happen, these magnetic moments inside the paramagnetic material will try to align themselves along the external applied magnetic field, right? So maybe this one will become like this, and this one along this one along the magnetic field, right? So what happens is that the materials gain a net magnetization along B, and if we denote the magnetization, which is a vector, is now parallel to the external magnetic field, right? And that's why usually for paramagnetic material, the susceptibility, which is defined as the free space permeability times the magnetization divided by external magnetic field, is a positive number, right? Because the magnetization due to the external magnetic field are in the same direction. Now if you look into the textbooks, there are different forms of paramagnetism, right? Now let me mention a few of them. We have Langevin or Curie paramagnetism, then we have Brillouin paramagnetism, then Pauli, and the last one is the Van Vleck paramagnetism, right? So my plan here is to discuss first 2 of these models. So let me begin first with the Langevin or Curie paramagnetism, right? And I will use a classical model to explain this behavior. So to start with, let's say we have a 2-dimension piece of a material, and we have some atoms, right? So in 2 dimension, you can understand, let's say we have some 4 atoms, and they are pointing in the random direction, some direction. If somebody asks you, how do you model all the direction that is possible in the random directions that are possible in 2 dimension, you will say that's a circle, right? If it is random, then we will have all the direction needed to cover the 2-dimensional space is a circle, right? So the same idea can be extended to 3 dimensions, right? And we need a sphere to cover all the angles, right? So the idea is that we have a piece of solid. Inside the solid we have a number of atoms or ions, and their magnetic moments are pointing in different directions, right? It could be random, and direction is random, so it could be any point in the space. To cover all the direction, we are assuming we have some sphere, right? And this sphere, you can see that has some axis, which is the z-axis, along this direction. And our idea is that we will apply our magnetic field along this direction too, right? So the z direction is the axis of the magnet. Now let us assume some annulus, right, over this sphere. And one thing is to point is that any magnetic dipole moments which lie in this ring, right, make an angle theta with the z-axis, right? So let's say we have, for example, some moment directed in this direction, right? So what is its, let's say its mu is the vector, right? So it's pointing some direction. And if somebody asks you what is the its component along z-axis, and you know the angle is theta, right? So the z component of the magnetic moment is nothing but the magnitude of this vector times cos theta, right? Because you can draw some right angle and you can see it along this we have mu cos theta, right? And if this is mu. So that's one important thing to remember, that we are trying to calculate the dipole moment along the z-axis, right? Okay. Now, the next thing that we should discuss about this structure, let's say we want to know that how many dipole moments are pointing along this annulus, right? So between the theta and theta plus del theta, right? Theta plus d theta. So there are a number of magnetic moments in this annulus, right? And you understand that if the area of this annulus goes up, the number also goes up, right? So let us find the area of this annulus, right? How do you find the area of the annulus? Let's say we know what is the width of this ring, right? Annulus. So the width is d theta, and we need to know about the perimeter of this ring, right? And what's the perimeter? That's like twice pi times the radius, right? And the radius is, you can see if this is r, let's say this is r, the radius of the sphere, then this bit is r sine theta, right? So, but r is 1, so we are assuming here we have a sphere of radius 1, right? Then r sine theta is nothing but only sine theta. So that's the area of this annulus, right? Area of some of the annulus. Now the question is, we are trying to find out that what is the fractional contribution of those moments who lie within this ring to the entire area of this sphere, right? So this ratio where we put the angular contribution, or sorry, the magnetic dipole contribution due to this ring, which is proportional to the area of the annulus, right? So we put the area of the annulus on the top, which is 2s pi sine theta d theta, divided by the area of the surface area of this entire sphere, which is 4 pi r square, right? But r is 1, that's just 4 pi. Then this ratio, right, usually is known by, from your geometry concept, is that the solid angle due to this angular strip, and this solid angle is nothing but let's say half sine theta. So we have half sine theta d theta, right? So you can think of this angular contribution is the ratio between those moments, right, that lie in this annulus to all the moments which lie in the entire surface area, right? So that's our solid angle for this problem. Okay. Now let me ask another question which I have discussed in one of the earlier lectures, that what is the energy of a dipole moment when you place it inside the magnetic field, right? So we are trying to calculate the energy of a dipole moment. So you remember, this is nothing but the dipole moment vector times the magnetic dotted with the magnetic field vector, right? So this is nothing but, if we expand the dot product, this is mu b cos of theta, right? This is the energy of the dipole in a magnetic field B. Now, I want to introduce one concept from statistical physics. I believe you came across this in your second year, is that what is the quantity known as the Boltzmann factor, right? So once you have the energy of the dipole moment, the next thing I am asking, what is the Boltzmann factor? You will see why I need this quantity. So usually the Boltzmann factor is defined as exponential of some quantity which is minus energy divided by the Boltzmann constant times the temperature of the system. That's known as the Boltzmann factor. Take it as a rule if you never come across this term, right? That's the Boltzmann factor. So in our problem, what is the value of the energy? That's like mu b cos theta, right? So let's put the value of E here. So exponent, this minus will be cancelled by this minus. We will have on the denominator is mu b cosine of theta divided by kbt. That's our Boltzmann factor. One thing I want to point at this stage is that you see we are bringing the discussion of temperature through the Boltzmann factor, right? And what is the purpose of temperature here? You have to understand that when you are trying to align the magnetic moments, right, by applying a magnetic field, the temperature is trying to randomize the direction, the alignments, right? Why? Because you understand when your system is at T temperature, you have kBT amount of thermal energy, right? That's your first year thermodynamics. So that amount of thermal energy will try to disrupt the alignment, right? That's why it turns out you will see that you need a higher magnetic field to align all the moments, because you have to beat the thermal fluctuation, right? So that's one important point to remember. And the temperature is we are bringing the temperature through this Boltzmann concept, right? Now let us understand another important concept from the study of statistical physics, which is how do you find an average value of some quantity, right? So we are trying to calculate some average value, right? And in this problem, the average we are trying to calculate is nothing but the average of mu z, right? What is mu z? Mu z is the, I told you, is the magnetic dipole moment contribution along z direction, right? And we want to calculate a thermal average, right? By putting an angular bracket, I mean it's thermal average, right? How do you calculate this value? This can be taken as a rule if you didn't see it before. So it's defined as a ratio first. That's the important thing. So what's in the denominator? Let me explain it first. In the denominator, you have to sum over, or you have to integrate over the Boltzmann weights or Boltzmann factors. So for this problem, this is our Boltzmann factor, right? And I am telling you to integrate this Boltzmann factor. Let's write it, the factor first. So what is the factor? This is E times mu b cos theta divided by kBT, right? Now ask yourself, in this exponent, which one is the variable, right? B is a fixed magnetic field. Mu is the magnetic dipole moment of some atom. It's fixed. Kb is constant. T is the temperature of your problem. Assume we are working at a fixed temperature. So all these terms are a fixed number, right? Then the variable is nothing but the theta. So when you want to integrate this quantity, this has to be over the angles, right? And the angles we use is the solid angle. Remember this as a rule. And we know the expression of the solid angle, right? From, I would say, this expression, which is half sine theta d theta, right? That's your denominator. Now the question is, what is the numerator, right? Okay. So the question to ask, what's the quantity we are trying to find out? Is expectation value of mu z, right? So this is the parameter of interest. On the numerator, you first put the value of the parameter you want to calculate, and you want to weight this parameter by the Boltzmann factor, right? Which is mu b cos theta divided by kBT, right? And then you want to integrate this product. The question is, again, the same concept. You have to integrate over the angle, right? And the angle we use is the solid angle in this problem, right? So that's how you evaluate the solid angle of the problem. And we will see in the future is that this way of thinking, the finding out the expectation value will lead us to find out the expression of the paramagnetic susceptibility. In the next lecture, I will show you how to evaluate these quantities and then explain the susceptibility of the paramagnetic material. So if you want to find these materials, you should look in this book, which is Magnetism in Condensed Matter by Stephen Blundell. I believe you'll find it in chapter 2, so it shouldn't be hard to find these things, right? I think that's about it, and thanks for listening.